In this video, we're going to walk through this solution to a practice problem around a manganese oxide and iron voltaic cell. So we have two reactions, half reactions, and I've copied the standard reduction potential from our standard reduction potential table for each one. So we have manganese oxide with a hydrogen atom, or sorry, cations, forming manganese +2 and water. And then we also have iron +2 forming iron, the element. And so I want to compare first the reduction potentials for these and decide which one's going to be my driving force. And so looking at these, my manganese being reduced, which shows that gaining of the 5 electrons will be a plus 1.51 volts. So when it's oxidized, its potential will be equal to negative 1.51 volts. Now I'll compare that to my iron. It's iron +2 being reduced to iron will have a cell potential of negative 0.45 volts. If it was being oxidized, that cell potential would be plus 0.45. And now of these, the one that is the largest positive number is, in fact, this reduction potential for the manganese oxide. So that's going to drive our reaction, which means that no matter what will happen spontaneously is manganese being reduced, or manganese oxide reduction. That means my iron is going to be oxidized. So remember, oxidized anode. So my iron will be oxidized. That makes this left-hand side of my voltaic cell that's drawn out my anode. And the right-hand side of my voltaic cell is going to be where the cathode is and where my reduction takes place. So looking at the reactants and products of my manganese half reaction, I could see that I have manganese oxide, which is an anion and aqueous, plus my hydrogen ions, which are also aqueous, and it's forming manganese +2 ions, which are also aqueous. And so we actually don't have a solid electrode in here. Instead, we're going to be driving that current through an inert electrode like a platinum wire. And what we should see is electrons and current travel from the anode to the cathode spontaneously. So if I wanted to write out my cell notation for this, I would have my, start with my anode side. So that's going to be my iron solid electrode, followed by my iron +2 in solution. This is aqueous. We can assume standard conditions, which will be 1 molar. And then I'll have my salt bridge. After my salt bridge, I'll have my cathode information. We'll start with the electrolyte solution for this. And so in this case, my electrolyte solution is what is being reduced, which is that manganese oxide. But it also is that H+ as well, which is in solution. So I'm going to use a comma and then put my H+ aqueous 1 molar in there as well. I have run out of room on the screen, but what would follow next would be a straight line. So I'll put that right here. And then we would put our electrode, which is going to be our manganese +2, which is aqueous and 1 molar, followed by our inert electrode, that platinum. And that would give us our cell notation for this. All right. So I think I just lost my screen. Second. All right, let's finish this problem. I'm sorry I lost the video. I could talk at length about how Zoom destroys phone battery. So now that we have our cell notation for our voltaic cell, we kind of know what's happening. Let's calculate the cell potential. So we're going to have our cell potential equal the reduction potential of our cathode minus the cell potential of our anode. And so I'm going to plug in, remember, these are reduction potentials I'm using. So I'm using the ones I pulled from the chart. So that'll be equal to 1.51 minus the negative 0.45, which is going to give me a total of 1.96.